In the heart of the atomic age, humanity unlocked one of nature's greatest secrets, the power of the atom. From fission reactors to hydrogen bombs, we've learned how to split atoms apart for energy. But what if we could go further, not just split them, but fuse them together as the stars do? Fusion, the process that powers our sun, represents the holy grail of clean, limitless energy. For decades, scientists have sought ways to recreate this stellar furnace on Earth. Massive magnetic confinement reactors, like tokamaks, and inertial confinement lasers, like those at the National Ignition Facility, have both come close. Yet both remain complex, costly, and just barely breaking even in energy terms. But hidden in the quieter corners of nuclear research lies a concept so elegant, so deceptively simple, that it could potentially revolutionize how we think about fusion altogether. Muon Catalyzed Fusion. Muon Catalyzed Fusion is not new, it's an idea that's been bouncing around since the 1950s, when physicists first began experimenting with exotic particles beyond electrons and protons. At its core, the concept is this: instead of trying to smash atoms together with heat and pressure, what if you could simply bring them close enough naturally, using the help of another subatomic particle? That's where the muon comes in. A muon is like an electron's heavier cousin. It carries the same negative electric charge, but it's over 200 times more massive. And that extra mass changes everything. When a muon replaces an electron in an atom, say, in a hydrogen isotope, it pulls the nucleus and the neighboring nucleus far closer than electrons ever could. Remember, the reason fusion is so hard is that atomic nuclei, both positively charged, repel each other with immense force. The only way to make them fuse is to overcome that repulsion by pushing them close enough that the strong nuclear force can take over. In stars, gravity provides that push. On Earth, we try to do it with magnets, lasers, and heat of millions of degrees. But a muon can cheat that system. Its heavier mass means it orbits the nucleus much closer than an electron does. In a molecule of muonic hydrogen, the nuclei can come within distances where quantum tunneling allows them to fuse, without needing the high temperatures of a plasma. It's a shortcut straight through the Coulomb barrier. To understand why this is such a big deal, let's look at the typical challenges of fusion energy. Traditional fusion reactors like ITER rely on heating hydrogen isotopes, deuterium and tritium, to over 100 million degrees Celsius. The plasma must be confined long enough for nuclei to collide and fuse, releasing energy. But achieving this balance between temperature, pressure, and confinement time, the so-called triple product, has proven extraordinarily difficult. Muon Catalyzed Fusion sidesteps temperature almost entirely. Instead of heat, it uses particle substitution to bring the nuclei close enough for fusion to occur naturally. When a muon binds to a deuterium nucleus, forming muonic deuterium, and then interacts with tritium, the muon draws the two nuclei close enough to fuse into helium-4, releasing a neutron and about 17.6 MeV of energy, the same reaction as in a typical DT fusion event. After fusion, the muon is released and can, in principle, go on to catalyze another fusion reaction. In theory, one muon could trigger hundreds of fusions before it decays. The process is beautifully compact, almost effortless compared to the fiery chaos of plasma fusion. The dream is that with enough muons acting as atomic matchmakers, we could generate steady, room temperature fusion power. So why aren't we already running muon-based reactors on every street corner? The devil, as always, is in the details. Muons are unstable particles. They decay in just 2.2 microseconds, an eternity by subatomic standards, but blink and you miss it in real-world terms. That means the window for catalyzing fusion reactions is incredibly short. Moreover, producing muons is no small feat. They're typically generated in particle accelerators through high-energy collisions, such as firing protons into a metal target. This process consumes far more energy than the resulting muon-catalyzed fusions can currently produce. It's the same paradox that has haunted fusion research from the beginning. We can make it happen, but not efficiently enough to make it useful. Even so, the concept remains tantalizing. Because muon-catalyzed fusion is fundamentally different from conventional fusion, it could complement other technologies rather than compete with them. In laboratory settings, experiments have confirmed that muon-induced fusion can occur at temperatures near absolute zero. It's not theory anymore, it's observed fact. The main limitations are muon production, energy loss per muon, and a phenomenon called alpha sticking. When a muon catalyzes a fusion reaction, sometimes it sticks to the resulting helium nucleus instead of detaching. When that happens, it's trapped and effectively removed from the reaction chain. If even a small percentage of muons get stuck this way, it drastically reduces the number of fusions each muon can facilitate. Physicists estimate that for muon-catalyzed fusion to become energetically viable, each muon would need to catalyze over 1,000 fusion events before decaying. In practice, experiments have achieved only around 100 or so per muon. Still impressive, but not enough to break even. That's why researchers continue exploring new materials, magnetic configurations, and reaction conditions to reduce alpha sticking and extend the muon's useful life. Some even speculate that under extreme magnetic or crystalline confinement, the sticking probability could drop dramatically, unlocking a self-sustaining chain of low-temperature fusion events. The potential applications of muon-catalyzed fusion, if fully realized, are staggering. Imagine small, portable reactors the size of a refrigerator providing continuous power to entire communities. No radioactive waste, no meltdown risk, and no carbon emissions, just clean, controllable fusion energy on demand. A spacecraft equipped with a muon-catalyzed fusion drive could generate enormous thrust with minimal fuel mass, potentially cutting interplanetary travel times to weeks instead of months. Even more intriguingly, muon-catalyzed systems could serve as scientific tools, miniature, contained fusion sources for medical isotope production, neutron generation, or compact plasma research. But before we can dream that big, the physics and engineering have to catch up. Modern particle accelerator technology is improving fast. Compact linear accelerators and muon storage rings are already being developed for neutrino research and next-generation colliders. These same tools could eventually serve as the foundation for practical muon generators. Some experimental proposals even suggest laser-induced muon creation using high-intensity light interacting with dense materials, a far smaller, more energy-efficient approach than traditional accelerators. If we can reach a point where muons can be produced and recycled cheaply enough, the entire energy landscape could change overnight. Interestingly, muon-catalyzed fusion also holds clues about the behavior of matter under extreme conditions. Because the process operates at low temperatures, it allows scientists to study fusion mechanisms without the confounding influence of hot plasmas. The data gathered from muonic atoms could refine our models of nuclear tunneling, quantum probabilities, and short-range nuclear forces. It's not just a pathway to energy, it's a window into the deep quantum structure of the universe. In that sense, muon-catalyzed fusion is both a scientific experiment and a philosophical one, pushing us closer to understanding the fine threads that tie together particles and forces at the smallest scales. Now, let's imagine what a future powered by muon-catalyzed fusion might look like. Picture compact, fusion cells, installed in homes and vehicles, each containing microgram quantities of deuterium and tritium. Inside, Muons generated by a small onboard source continuously catalyze fusion events, producing enough electricity to power everything from cities to spacecraft. Maintenance would be minimal, just fuel replenishment every few years. The global grid would dissolve into a network of self-sufficient nodes, each generating its own clean power. Wars over oil or lithium would vanish, replaced by an era of energy abundance. Climate change would slow to a halt as fossil fuels fade into obsolescence. Humanity could finally step confidently into an era of sustainable civilization. But beyond energy, the implications stretch further. If muon catalyzed fusion becomes viable, it would revolutionize propulsion. Deep space missions could use fusion engines fueled by light isotopes, generating thrust through direct energy conversion. Imagine ships coasting between planets powered by fusion reactors no bigger than an SUV engine. Colonies on Mars could use these reactors for power and fuel synthesis, reducing dependence on Earth. Even asteroid mining operations could employ portable fusion generators to melt and process ores in situ. This is not the realm of distant science fiction, it's a logical extension of physics we already understand, waiting for technology to catch up. Of course, skepticism is healthy. The energy economics must make sense, and right now, they don't. Producing muons still requires particle accelerators consuming gigawatts of electricity. The challenge is breaking that cycle, creating a self-sustaining system where the energy output of fusion reactions helps generate new muons in a closed loop. Some theorists have proposed using the intense neutron flux from fusion reactions to drive secondary processes that generate fresh muons. Others suggest hybrid designs, combining muon catalyzed fusion with magnetic confinement to amplify yield. If even one of these designs proves efficient, it could open a doorway to practical, continuous muon-driven reactors. The story of muon catalyzed fusion reflects a broader truth about scientific discovery. Progress often begins with elegant, almost magical simplicity, but the details are where genius and perseverance meet. Just as early chemists imagined alchemy transforming lead into gold, modern physicists chase the dream of turning hydrogen into sunlight. It's an ancient desire, written in our myths and aspirations, the idea that we could harness the same forces that light the stars. Muon catalyzed fusion is one of the most beautiful embodiments of that dream. It doesn't rely on brute force, but on subtlety, replacing a single subatomic particle to unlock a cascade of energy. As the 21st century unfolds, and as global energy demand continues to rise, technologies like muon catalyzed fusion remind us that the answers to our biggest problems may lie not in building bigger machines, but in understanding smaller ones. Particle physics is entering a golden era of precision, where quantum control and nanotechnology converge. As we learn to manipulate individual particles with lasers, traps, and magnetic fields, the barriers that once made muon fusion impractical could crumble. We might discover ways to extend muon lifetimes, reduce alpha sticking, or even create stable, muon-like particles through exotic field interactions. The deeper we probe into the quantum world, the more it rewards us with new tools for shaping the macroscopic one. So, while muon catalyzed fusion isn't yet ready to power our cities, it stands as one of the most promising and elegant pathways toward that future. It represents a different way of thinking about energy, not as something that must be extracted violently from nature, but as something that can be coaxed gently from the very structure of matter. The muon, fleeting and mysterious, shows us that sometimes, the key to harnessing the power of stars lies in the smallest shadows of the subatomic realm. It's a testament to human curiosity, that even a particle that lives for 2/millionths of a second could hold the secret to our civilization's next great leap forward. And perhaps, one day, when we flip on our fusion-powered lights, we'll remember that it all began with a tiny particle and a simple question: What if there's an easier way to fuse the atoms of the universe? Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.